we started the last unit by thinking about what happens when you put an inductor in a circuit. So we had a battery and a switch and a resistor and an inductor. And we talked about when you close the switch, current will flow, current will create a magnetic field in the inductor. That magnetic field increases in time, so Faraday's law would predict a back EMF. And we thought about how that will affect the circuit. So now we really just want to do this mathematically. So let's label that R, let's label this L, some inductor with inductance L. And the way to do it mathematically is Kirchhoff's loop rule. All right. So we've done this for just simple resistive circuits. We've done it for RC circuits where you have a resistor and a capacitor. Now let's do it for what we're talking about now, which is RL circuits, resistor, inductor. Okay, well, Kirchhoff would say start here, go around the circuit, and all the delta V's should add up to 0, right? So if we go from here to here, that's low to high, so that's EMF of the battery. And then we can assume the current's going to go that way, we're looping that way, and that means this would be the high side of the resistor and the low side if the current flows that way, so it's minus IR, like that. And then we know this is going to be a back EMF, so we would say minus L di dt. And you get back to here, back to 0. So that is Kirchhoff's loop rule for the RL circuit. And it's wrong. You should not do this. A big no. No. No, no, no. Most books do this, but it is not correct. Okay? This is completely wrong. You can't apply Kirchhoff's loop rule to this kind of a circuit. Let's think about what is Kirchhoff's loop rule really saying. It's really saying that the integral around a closed loop of E dot dl equals 0. And that's true in electrostatics. We know that the electrostatic field is conservative. If you have a charge here making a big field and you start here and you move around and you go back to here, the same place, the potential difference should be 0, right? Because the potential is well defined with a constant value everywhere in space. However, this is not true when you have currents changing in time, especially when you have inductors. And you always have a little bit of inductance, right? The circuit itself is a loop, right? So really, anytime the current changes, you're going to have some inductance. Now, you have a much bigger inductance if you actually put an inductor there. So what we got to do is do this the right way. Okay, so let's think about the right way to do this.